Hi, I'm Smita Lokhande from TCS Research. So today I'll be presenting my paper Continuous Intraday Market Trading Model for a DR aggregator. This work is carried out with my colleagues from the team from TCS Research. So as we know, there is an increase in the penetration of distributed energy resources like solar PVs, wind farms, electric vehicles, energy storage systems in the distribution side of the network. These DRs can offer clean energy, and as they are flexible in nature, they can provide various services like balancing services, reserve services to the grid if they are operated in a coordinated manner. So this is where aggregator is emerging as a new player in the market. An aggregator's role is to coordinate multiple DER assets and provide services to the system through appropriate markets. So DERs are stochastic in nature, and the uncertainties associated with them are usually higher than the conventional load and generation sources. Hence, they are better suited for markets that operate with a shorter lead time, like the intraday markets. So there has been substantial research that focuses on DRs trading into intraday markets, either exclusively or in combination with other markets. While there are notable contributions in this area, many of the models proposed possess one or more of the following gaps. Some of them do not model the continuous price fluctuations of the volatile intraday markets. Heterogeneity in the nature of DRs is usually not considered. Many of them do not model for the constraints placed by the network operator for injecting or withdrawing power at the network buses, while some of them do not provision for energy exchanges to happen within the DR pool. So in this paper, we have tried to address these gaps, and we have developed an approach to find an optimal trading strategy for aggregators managing a heterogeneous set of DRs to trade into intraday markets. Some of the specific contributions of our paper are: we model the price volume behavior of the intraday markets as a 2D distribution, which is used for optimizing the bids submitted in the market. We formulate the bidding problem as a potentially non-convex mixed integer nonlinear programming problem. As MINLP is complex in nature, we have proposed two relaxations. The first relaxation removes the integer variables and converts it into a pure NLP problem, while the second relaxation removes the complex nonlinearities and converts it into a MILP problem, which is solved in an iterative fashion. These proposed techniques are tested against a widely used method based on the ID3 based distributions. So this is the model of our proposed, this is the setup of our proposed model. The model takes in the necessary inputs, runs the optimization, and uses the output to place optimal bids in the market. The inputs to the model consists of the DR forecasts, which include forecasts of generation and demand, and also the technical characteristics of the batteries. Second input is the historical data of the intraday markets, and the last input is the network data, which includes mapping of each DR asset to different nodes in the distribution system and the limits on the export and import at each node. Using these inputs, the aggregator runs an optimization model whose objective is to maximize the profit earned by placing bids into the intraday markets, and this bidding is constrained to the technical characteristics of the DR assets, the behavioral preferences of these assets, and the network constraints. We'll go through this optimization model in detail in the upcoming slides. And once the optimization is implemented, the output is viewed on two levels. On an aggregate level, the output tells how the aggregator should participate into the market, that is whether it should place a buy bid or a sell bid for each of the delivery slot, and the price volume pair that should be submitted for each slot. And from an individual asset point of view, it gives an direction as to how to operate and control each of the DR individually. In the proposed aggregator model, we assume that the subscribers have one of these three DER assets, a solar PV, demand and flexible load, and batteries as the energy storage systems. So as we are trading in intraday markets, for a trading time T, we assume that the aggregator can place bids with a lead time of R for tau consecutive delivery hours. So these tau consecutive delivery hours is called as an optimization window. As we can see from this figure here, at time t, the optimization window will start at t plus r and it will continue till t plus r plus tau. So the aggregator can place bids for all of the tau consecutive hours when trading at time t. And also this optimization is run in a moving window fashion, which enables the aggregator to take into account the revisions of forecasts and the market conditions to place better bids in the market. We'll first discuss the constraints and then we'll arrive at the objective function of the formulation. So the first set of constraints corresponds to market and pool trading. So this decides the volume to be traded into the market, which is X, and the volume to be traded in the pool, which is X pool, and it depends upon the presence of generation and the demand at each node. When trading within the pool, care is taken that there is a balance between the energy exchanges happening in the pool, and also trading at each of the node is limited by the maximum and minimum limits, which are usually communicated by the network operators. The second set of constraints are the battery constraints. It involves calculation of SOC for each delivery hour while limiting them to its maximum and minimum limits. And the last two equations correspond to the maximum charging and discharging rate constraints of the battery. The R charge and R discharge is the maximum charging and discharging rate, and it is usually a function of SOC of the battery. Hence, these two constraints are nonlinear in nature. Also, it has a binary variable Z, which is required because this it is necessary that the battery either charges or discharges in 1 hour and does not do both. The next two equations are the constraints required for scheduling of the flexible demand. The formulation also allows for trade volume revisions, which is given by this constraint. So here QB clear and QS clear are the quantum of buy and sell commitments made in the previous optimization windows. So while calculating the aggregated power H stored for every delivery hour H, we consider the previous commitments and the nodal market power, and this H store can be positive or negative. If it is positive, it means that the aggregator has excess generation and it needs to place a sell bid into the markets. If H store is negative, it means that the aggregator has excess demand and it needs to place a buy bid. So this decision of placing a buy bid or a sell bid is taken care by the binary variable delta as shown in these three equations. If we see these two equations here are nonlinear in nature and they can be linearized by standard conversion technique, and hence these two equations are replaced by the set of these five equations which make the constraints linear. And the last set of constraints is limiting the sell prices and buy prices between its maximum and minimum limits. The values of the decision variables must be determined so that the revenue earned by the aggregator through trading is maximized. So the objective function shown here has two parts. The first part relates to sell bids, the second part relates to buy bid. And here we have two terms, capital F sell and capital F buy, which is the market's propensity to clear a bid PH and QH submitted to the markets, and it is calculated using the variables FTH, which is the 2D distribution obtained from the cleared price volume behavior of the intraday markets. So this 2D distribution is nothing but the conditional probability of finding a PQ transaction in the bids cleared at time t for delivery hour h. Now as we want to maximize the revenue, the sell profit is multiplied by capital F sell, while the buy cost in the second term is multiplied by 1 minus capital F buy. So this is done because we want the optimizer to place bids which have higher probability of clearing and not place bids at price so that the cost is lower but the probability of clearing is also lower. So in this way, as we can see, the objective function is nonlinear in nature, and thus the entire formulated problem becomes a mixed integer nonlinear programming problem. MINLP type of problems are usually NP hard, complex, and difficult to solve using conventional solvers. Hence, we have proposed two relaxations to obtain simpler version of the original problem. The first relaxation is converting this problem into a pure NLP problem. In this conversion, we relax the binary variables and replace it with suitable other relaxations. So the first relaxation is the variable Z, which was present in the battery charging and discharging rate constraints. So if we assume that the battery charging and discharging rates are independent of its SOC level, Z need not be introduced into the formulation. It can be replaced by a continuous variable R, such that if R is greater than 0, it will indicate that the battery is charging, and if R is less than 0, it will indicate that the battery is discharging. So the original set of battery constraints can be replaced by these two new constraints, wherein the constraints become linear and we get rid of the binary variable ZH. The second relaxation is of the binary variable delta H, which was required to make a decision of placing a buy bid or a sell bid. If H tot is greater than 0, delta H is equal to 1, which corresponds to a sell bid. If H tot is less than 0, delta H corresponds to 0, which means that the aggregator should place a buy bid. So this behavior of delta H can be approximated through a sigmoid function defined on the value of H tot as shown here. H tot is multiplied by a very large value K, so that care is taken that by this function, sigmoid function, exactly mimics the delta H value while remaining continuous, and we do not need delta H anymore in the formulation. So in this way, by relaxing both the binary variables, we convert the original problem to a NLP problem, which is comparatively easier to solve. The second relaxation approach is to convert the original MINLP problem to a MILP problem by relaxing the complex nonlinearities. So nonlinearities were present in two places. The first nonlinearity was in the charging discharging rate constraints of the battery, which can be linearized as discussed earlier. The second nonlinearity is present in the objective function. So the nonlinearity here can be relaxed by first converting the bivariate terms into univariate terms and then implementing a piecewise linear approximation of each of the term. So for doing this, we decouple the objective function into two problems, problem A and problem B, and then we solve them separately in two steps. So this is done in the following way. So in step 1, we initialize the prices PS and PB so that the objective function becomes a function of the variables QS and QB. We solve this problem A in step 1 to obtain the values of QS and QB, and using these optimal values QS and QB, in step 2, we solve the problem B to find the values of PS and PB. So these two steps are simulated iteratively till the error between the decision variables in the consecutive steps is below a particular threshold value. The iterative procedure to solve the MINLP problem by relaxing the nonlinearities is shown in this flowchart. So for one particular optimization window WT, we initialize PS and PB, we linearize the battery charging and discharging rate constraints. Then we compute the piecewise linear approximation of each of the terms in the objective function and solve problem A to obtain the values of QS and QB. Then we use this QS and QB values as initial values in problem B and solve it to find the values of PS and PB. And then we compute the difference between the previous two versions of all the four variables. And if the error is within the tolerance, we exit this iterations, or else we continue with the iterations till the error between the previous two versions of all the four variables is below a certain tolerance level. So in this way, the original problem can be converted to a MILP problem, which can be solved using an iterative fashion to obtain a similar optimal value. So the distrust aggregator model has been implemented on a small set of DRs of 50 assets, which are located at different nodes in a IEEE bus 13 IEEE bus 13 bus radial system. Real world data of Apex intraday market in France has been used for simulation. The optimization window is considered to have 6 hours with a lead time of 2 hours. Solvers used are the open source solvers of GLPK and IPOPT, and the forecasting methods for forecasting the generation and load is the stat LSTM model, whereas the 2D distribution, that is small FTH, is forecasted using a persistence model. And the proposed two techniques NLP and MILP are compared with a baseline technique, which is the ID3 price based technique. So in this technique the entire formulation is same, only difference is in the objective function. So we initialize the PS and PB values to the ID3 price values, and we equate the propensity of market clearing to 1. And these three techniques are compared using two metrics. The first metric is the net revenue earned by each of the technique, and the second one is the computation time required for solving one optimization window. The revenue earned for each of the day is shown here for different cases. So if we see in each of the case, the revenue inflow and outflow under the two proposed technique, that is NLP and MILP, is always better than the baseline technique of ID3 based bidding. So in terms of numbers, NLP always performs better than MILP, which is then followed by our baseline technique. For some days NLP may be performing better, for some days MILP may be performing better, but overall both of these proposed techniques have higher performance than the baseline technique. And if we see, the baseline uses an optimization formulation which is similar to our proposed technique. The only difference is in the objective function. So the objective function in the baseline does not use the joint price volume histograms, and this shows that modeling of the dynamics through the price volume histograms helps in designing better trading bids. So in order to understand how the 2D distribution helps in improving the performance, we have plotted a heat map of buy bids for one simulation day for all of these three techniques. So if we see for NLP and MILP, the prices are always less than 30 euros, whereas MILP prefers bid with higher prices. And also the volumes, the quantity of volume is very high for baseline bids, whereas NLP and MILP prefer bids with smaller volumes. So bidding with smaller volumes at lower prices ensures that these two techniques have flexibility in pricing the volumes differently, so that probability of clearing is higher for both of these techniques. The propensity to submit bids at lower prices and still be cleared in markets is successful because of the information possessed in the 2D histograms of the price volume behavior of the markets. So if we see here, we have the histograms for delivery hour H and delivery hour 23. These two hours have the same ID price, but if we see the behavior in the markets is very different for the two trading hours, that is H-7 and H-4. Hence modeling this behavior into our formulation helps the aggregator in better designing of the bids. And we have also simulated our proposed technique under a case of high generation, in which the solar size was doubled while keeping all the other parameters same. And under this scenario also, it was found that NLP was the best performing method, followed by MILP and then the baseline technique. So this shows that the formulation is pretty reliable. In this formulation we have modeled pool, such that the aggregators can help each other and exchange energy among themselves. So this plot shows that modeling of the pool increases the performance than the case where pool is not modeled. The second metric is the average computational time required for solving one optimization window. So if we see, as the number of the DR assets goes on increasing, the number of variables also increases. the time required for a reasonable size of DR 500 DRs is 35 seconds for NLP, whereas 15 seconds for MILP, which is a pretty reasonable time, whereas the original MINLP problem was not solved even for a small set of 50 DRs. So this shows that the two proposed techniques are scalable and can be used for a larger data set as well. So overall in this paper we have proposed an optimal bidding strategy for an aggregator to maximize its revenue by trading into intraday markets. We have proposed two approaches which who give optimal schedules without any significant loss of accuracy. They decrease the computational times and also encourage scalability. In future scope, we intend to extend the model to enable simultaneous trading between the intraday markets and real-time flexibility markets. Also, we intend to consider flexible generation, the flexibility activation costs, and the interdependency of the flexible demand across several time slots. Thank you.